Good morning everyone, nice to meet you. My name is Khaled Lounnas, a PhD student from University of Science and Technology Huari Boumediene. I'm very happy to present to you my research paper titled Toward an Automatic Dialect Identification System for Algerian Dialects using YouTube videos. I will begin the presentation by defining the research issue, outlining research gaps, and mentioning the major contribution. Next, we will give a summary of the corpora that we utilized to help us build the model, as well as some statistic and comparison to the well-known Kalam DZ corpus. Once completed, the next part will present the system's methodology scheme, along with a number of important features and classifiers. In the result and discussion section, we analyze the suggested approach, particularly the acoustic-based and spectrogram-based approaches, using two typical metrics, accuracy and F-score. And while doing so, we describe how segment time may be used to assess system performance. Finally, we finish the presentation with a conclusion and future works. So, speaking to one another directly is the most natural form of communication across all media. The study of voice processing has drawn increased interest from the scientific community, particularly for low resources languages like Arabic and its dialects. These problems are highly fascinating. Algeria's dialect, despite its richness and diversity, doesn't meet linguistic standard, since it departs from standard Arabic and has a vocabulary drawn from several sources. We have a problem of lack of resource. So very few studies on Algerian dialect have been completed, and little at all have been done on such dialect. As a result, automated dialect detection is the first step in carrying out many natural language processing tasks, such as speech translation, opinion mining, and so. The main contribution of our works is building a bridge of connection across various Algerian regions, the creation of a system that can automatically identify spoken languages using a range of machine learning and deep learning techniques to encompass 23 classes of Algerian dialects learned from YouTube videos. Any engineering system must go through a typical corpus building phase before it can be developed. Therefore, any machine learning based model must succeed by amazing sizable corpus. Because of this, and in an effort to solve the main problem mentioned in our previous study, we made an effort to build a large corpus that included the majority of Algerian dialects. In the next 3 slides, we will devise a recipe for building large-scale speech corpora by harnessing web resources, namely YouTube. So here, because our corpus only has 23 cities, there are only 23 subdialects. We have various dialects from the center, west, and east that are presented in table 1, with clip ranging in length from 2 hours and 7 minutes to 2 hours 42 minutes for each dialect. It should be noted that this is one of few work to our knowledge that build an Algerian speech corpus for dialect identification, where the first corpus is named Kalam. In Table 2, which highlights the number of subdialects, overall duration per subdialect, pre-processing process, source of data, number of speakers per file, we compiled our corpus to Kalam DZ. Even though our corpus is smaller than Kalam DZ, there is one difference. Our emphasis was on YouTube videos with extremely little background noise and no music. Here the table 1 dot represent some statistic about our geographical regions, and table 2 present a comparative study between our corpus and the well-known Kalam DZ corpus. The entire structure of our method for the automatic identification of Algerian dialect is shown in the schematic in figure 1. The architecture is organized as a series of concurrently running process: data collection, pre-processing segmentation, future extraction, which are represented by acoustic and spectrogram approach, model training, and finally system evaluation. For the sake of our research, we are only interested in two types of audio: categorization, classification based on acoustic parameters, and by spectrogram. One of the simplest forms of data that may be directly extracted from unprocessed speech during the speech parameterization process is acoustic data. Acoustic data can also be used to recover higher level speech information such as phonotactic and word information. And word information may also be retrieved from acoustic data. We utilized a process based on LibRosa which incorporates spectral and rhythm properties with a total of 193 components, include Mel frequency spectral coefficient, tones, Mel spectrogram, chroma vector, spectral contrast. These features served as the training data for both support vector machine model as well as a convolutional neural network. The aim of this research is to develop a system for categorizing audio files and determining which category they fall under. That means dialect. By examining the spectrogram which associate an intensity or a power with each frequency, we may categorize the audio from an image. This problem may be used in a number of real-world situations, such categorizing music video to detect the type of the music they include, or analyzing brief statements made by a group of speakers to establish who is speaking based on their voice. The following two slides show how to set up and test our suggested system, in which we can see after collecting the video samples, we converted them into waveform using a well-known tool, FFmpeg function with a sampling rate of 16 kHz. For noise suppression, we utilize the well-known based LibRosa tool named Noise Reduce at the pre-processing stage in order to compare three different case study. We splitted our speech data into segments of 3 different duration, 5, 10 and 20 seconds, which will serve as the input data for 3 different models. We utilize the function presented in the browser library to extract the aforementioned characteristic. Each audio files of our corpus will go through this procedure, with the features being stacked vertically in one array vector and the labels in another. Both vectors will be stored in 2 file format, features.numpy for the features and labels.numpy for the labels. At the end of the feature extraction procedure for later use. After feature extraction stage, we divide our data into training data and test data, each comprising 18% and 20% of the corpus respectively. We use the sklearn package with the default parameters to build our first support vector machine model. Concerning the convolutional neural network, we will initialize our model as follows in the following figure. Table 3 represents Algerian dialects identification based on acoustic features. The reported result before and after pre-processing. The best F-score obtained are in bold. For 5-second segment, we see that both algorithms are raw data result are actually superior to those obtained from pre-processed data. For the 10-second segment, we see that the convolutional neural models prediction for pre-processed data are marginally better as compared to the raw data. However, the support vector machine model with raw data surpassed the pre-processed data results by 5%. The raw data results outperform the pre-processed data for 20-second segments for both algorithms. We find a minor decline in performance for the pre-processed data, which is related to the fact that it is not as good as the raw data, which is due to the noise removal loss. Whereas the table 4 represents the result obtained by classification of spectrogram-based images using visual geometric group with size layer pre-trained model. The best epoch for each duration is reported. According to the result shown in table 4, recognizing dialect with spectrograms perform best with 20-second duration data with a macro F-score of 88%, while score for 10 seconds and 5 seconds audio are 18.4 and 15.7 respectively. These results are acceptable since the audios in the 20 seconds include more information than the audios in the 5 seconds and 9 and 10 seconds respectively. We observed that the length of the audio file may influence the number of epochs required for the convolutional neural network model, with 5, 10 and 20 seconds requiring epoch 3, 5 and 20 respectively. To recap, despite being well known for its high accuracy in image classification, the pre-trained visual group model could not reach the desired result. By comparing the performance between acoustic and spectrogram approaches based on the collected result, we discovered that the acoustic-based method outperforms the spectrogram-based approach by around 10%. This allows that the auditory characteristics are more reliable descriptor for discriminating across dialects. minimizing confusion and delivering better results. When compared to what is accessible in the literature, the obtained conclusions are fairly good. Our contribution to this work is that we worked with 23 Algerian dialects. To recap, this research focuses on the creation of an automatic system for recognizing Algerian dialect. To attain our aim, we employ two approaches. The first based on acoustic features derived from audio, while the second is based on spectrogram features. The two approaches have been evaluated using support vector machine and convolutional neural network for the first one, whereas a transfer learning technique was applied for the second approach respectively. This model was evaluated using audio duration 5, 10, and 20 seconds. The result for 20-second duration data using convolutional neural network were extremely good, with an accuracy of 98.09% for the raw data. However, it should be highlighted that while employing a spectrogram to train a VGG deep learning model, our proposal performed best when the size of the audio voice was significant. Its meaning 20-second segment. The previous experience with 23 Algerian dialects stresses the relevance of acoustic parameters and the use of spectrogram in differentiation Algerian dialects. Future research may try to add new dialects and cities to our current corpus in order to eventually encompass all Algerian dialects. In addition, we will investigate deep learning methods to improve the modeling of Algerian dialect. Finally, we will look for optimal duration that will allow our system to generalize more effectively. Thank you for your attention.